Clotilde Fermanian will talk about semiclassical analysis in filtered manifolds.
Okay, thank you for the introduction. Thank you for the invitation. It's great to be there. I have to go under Newton's apple tree to see if the spirit is inspiring. So the first thing I have to do, I guess, is and an introduction is to say what is a filtered manifold. Okay. So I take a manifold, a smooth manifold of dimension n, and I say that it's filtered if I have a nested sequence of subspace of the tangent space, which to what thing. So I start with 0. This is my h0, which is included into h1, some hr, so I have r steps in my construction, and the last one is the tangent space. So I have my manifold. We can think to it as a compact manifold, but it's not necessary. And above x point, the tangent space is decomposed in that manner. Okay? So it means that I have a sort of hierarchy between my vector fields, which are in my tangent space. They can be there, they can be there, they can be there. They are somewhere. Okay? And that's a way of differentiating the vector fields. And I assume that this is compatible with the Lie bracket, so meaning that when I take gamma of hi, gamma of hj, I compute, I take one vector a, one vector here, the commutators arise in gamma of hi plus g. Okay, so it's compatible with the Lie brackets of vector fields. Yeah. So the main example is contact manifolds.
What is gamma of h?
You take vectors of hi and you compose together, but you take a linear sum of this hi. If you prefer, you take one vector here, so I can write it like that. The I, g belongs to hy plus g. So I take vy in hy, so in a point x.
Oh, okay.
Okay, vg in a point x, and then the commutator arrives exactly there. Okay, so this is above each point x. You have decided that your vector fields are different. They are different level in some sense. Okay, it's clear. And the main example maybe is contact manifold, where there is in the tangent space there is the horizontal distribution, which is.
And if I plus j is bigger than r?
Yeah, exact. So I assume I take by convention that for r bigger than r, I say that I check service. Thank you. You have to be careful with me. I am forgetting things. Yeah. Okay. So I rely on you. So for contact manifolds, you have this horizontal distribution, and then the full space is just t plus what I call t, which is obtained by commutation between d and d, and this gives all the tangent space to the contact manifold. Okay, so this is a basic example when r equal to. And in your vectors, you have above x point x, you have an horizontal distribution, so a sort of vector fields, a range of vector fields. The dimension here is something like 2D, and the dimension of t is 1, usually. And so your contact manifold is of dimension 2D plus 1. So it's an odd number. Yeah. So this is a sort of manifolds which enter into the range of filtered manifolds. So M is a filtered manifold if I have this sort of manifold. Yeah. So I can give a basic example. So I take for M R3, okay, and I say the vector space. I have one precise one which is dx, another one which is dy plus x dz, and then z equals dz. Then d is generated by dx by x and y. Okay, and t is just factorial. Okay. This is okay? So one can ask, why are we interested in filtering manifolds if we do PDEs? And there is one reason is that I have written my vector fields with dx, dy, dz as a basis. Okay, so like it's some operator or order 1 operators. So this vector, they can just come because you want to analyze, I call it delta minus delta m here. Equals, so it's not a okay, it's almost a Laplacian, but I take just x squared plus y squared. So it's a sum of square, dx squared plus dy plus x dz squared. Okay, I mean, if this is the operator that you want to treat or we want to work with it because it's in your PDEs, then okay, this vector field x and y will play a pretty special game. Okay. And so we will see more about it later. But for example, a typical problem that people look at is that you assume that M is compact, and you take some operators in the first strata, or maybe just in this. Okay. We take filtered compact, and then you assume that you take a basis of the first strata, H1, which is, I mean, you take a frame above each point. So by this I mean, so N1 is between 0 and N. Okay. And if I assume that by commutators of H1 I get all the vector fields, but some operator which is reasonable to consider is I call it minus delta m, like here, the sum of square, x1 squared plus x2 squared plus xn1 squared. You get a compact operator, and so you get an operator which has compact resolvent because my m is compact, and then you can look to the sequence of eigenvalues of this operator. Okay, so this is some question that has been addressed a lot in the Riemannian context. There is a sequence of eigenvalues which goes to infinity. Okay, so the phi n in H2 of m can be normalized. Okay, and the questions that usually people are interested in, at least in the Riemannian case, is to say something about these quantities, or at least. So I take some compactly supported function. I mean smooth because of my manifold is compact. And I look to the evolution of these quantities, and I wonder what happens when n goes to plus infinity. So this is a question that has been addressed a lot in the Riemannian case. So the Riemannian case, by this I just mean that my filtration has only one step, which is H1 equal Tn. So in that sense, when I take all the first directions, I get exactly the standard Laplacian. So if you look to these quantities, the fundamental results from quantum ergodicity is to find conditions dynamical conditions on the manifold, under conditions on M, so that you know something about the measure which is describing this limit when n goes to plus infinity. Or so the limit here, more or less, we are looking for a measure because this is the probability density, and we are looking to the weak limit of this probability density. Okay. And so find for determining the limit, the weak limit, because I'm testing against some a of phi n of x squared. Okay. So the point is that for the Riemannian case, one knows that if the ergodic flow is ergodic, if the geodesic flow is ergodic, then you have you can describe that this limit is the Liouville measure on the manifold. Okay, so this is the Schneiderman problem. Schneiderman problem. It's an old problem for the 70s. I think I have a precise date here. Okay, which has been solved by Clotilde Fermanian in 1985 and by Zedlich. The paper is 1987, but I think they did it simultaneously. Okay, and the proof, in fact, is not involving only functions of x, but you need to know how you need to study the oscillations of your function phi n. Okay, so microlocal proof, or I should say maybe semi-classical proof. Semi-classical proof. And what I mean by this is that I know how my functions are oscillating. I know that if I take Laplace operator of phi n, it's small as it's large like lambda n. Okay, so the oscillations are more or less of the size 1 over the square root of lambda n. In the Euclidean setting, if I know that the Laplace of phi n is like lambda n, when n goes to plus infinity, I know that the derivatives are of size exactly 1 over square root of lambda n. Okay? So maybe I should not write it like that, square root of lambda n. So what is done in the... So this was the Riemannian case, and in this let's say, if I take my operator here, which is not containing the z square, so it's a sub-elliptic operator. I will explain later what it means. In the sub-Riemannian case, which consists of, for example, for a contact manifold, I should say, there are very few results, and at least there is only results for contact manifold. Okay, and the first one has been given by Clotilde Fermanian, Hilary and Trella. And it's a result from 2018 for d equal 1 here. I mean, contact manifold. So some contact manifold of dimension 3. Okay, dimension 3. They give a condition. They say that some flow, if the red flow, so the red flow would be something which is along t. Okay, if this flow is ergodic, this gives a condition for this allows to determine exactly the weak limit of these quantities. Okay, so this is a very strong result, giving conditions for quantum ergodicity. Okay. So there are this result. There is another one which isn't published for the moment from Nikhil Saval, who is treating quasi-contact manifold. Okay, the same sort of result relating the quantum evolution and the dynamical questions is giving a condition on the flow. Yeah?
So the definition of contact is through this filtration?
Yeah, for a filtration which has only two. Yeah, exactly.
Filtration of
like
only
this.
2 steps?
Only 2 steps. Huh? So, and this sort of property of 2d plus 1, even an odd dimension. Yeah, and you need I mean, maybe I have forgotten to write something, but I'm not completely sure. Maybe there is an expert in the room, very school. Luc, I have forgotten something in the definition, or is it?
But if it's odd dimension, how can it be tangent space?
How? The tangent space. The manifold is 2d plus 1, there is a tangent space in it. And in this point, so the tangent space is dimension 2D plus 1. This is M, the N that I had before.
Oh, the N is 2D plus 1.
Yeah, exactly. Yes.
Not the M.
Yeah. It's okay? Okay, questions? Okay, so I was saying that Riemannian case is known, I mean, since the 80s. And in the sub-Riemannian case, and at least in the contact manifold case, there is this result, which is very strong, of Clotilde Fermanian, the first one. Yeah. There are some attempts on the quasi-contact case, and there is a recent paper of Benedetto.
Can I?
Yeah.
One more question?
Yeah.
You had two types of Laplacian M. One had just the two vectors, and one had all of them.
Because this was in the case of the example, typical problem. So this is example.
So in the contact manifold case, my Laplacian
is that one, the contact.
Without the
because there is only
without the rib flow.
Yeah, without the rib flow. That's the point. There is no dz squared plus dz squared, and the fact that there is not the rib flow is not a problem because these two guys, when they commute, they generate the rib flow. Yeah. Yeah, up there. Yeah, I need more than what is written there. I need that the first strata, H1, is generating all the tangent space by the Lie brackets. All the tangent space by iterated commutators. Okay, I would say that this is a sort of stratified case, and this one is just graded. I mean, what could happen is that in H1 there is new vector which is not arriving from a bracket of two vectors. In H2 there is something which arrives and which is not a commutator of two vectors of H1. Yeah. So if I consider this operator, and if I want to have a nice description and so on, I need to be sure that all my directions are controlled, in the sense that if I pick some xi, I can find it back by commutating this n1. Yeah. We will come back to this condition in a few moments. So what I want to explain today is how, so the result of Benedetto, he takes a contact manifold, he had some structure condition, which is geometric, but I will not detail. And in that manner, he can extend the result of Clotilde-Fermanian to any dimension. So okay, he's adding some geometric property, and he's able to treat higher dimension. Yeah. But why I want to cite it is because, I mean, he's using really different techniques here. And this is the thing that I would like to explain, how the techniques there are different from that. Yeah. And just to explain a little bit more and conclude this introduction. So I said that this problem, in fact, is not very well posed because it's just addressed in the position place, in the M. You see, I am testing function against a of x, and I am not seeing what happens in terms of oscillations of the function. I am not involving the derivatives. Okay, and the proof of Cologne-Verdier and Zedich theorem, I should say classical proof, standard is a bit weird. No? So the classical proof of this result, you replace this problem here, more or less, by looking to some operator which is going, you take something in L2, these quantities are your favorite quantities, but here you need to add something which is a pseudo-differential semiclassical operator, and I'm going to write what it is immediately. Semiclassical operator, which means that your A is now a function in two variables, Rn times Rn, because I'm going to look to the position and the impulsion simultaneously in terms of quantum mechanics. So what is it? So in Rn, if I was in Rn, my operator, when I let it apply on the smooth function, the Schwartz function, not to have any problems, it's just doing this thing. So you take your function f of y, f, okay? If I just do this with my function a of x, which is anything, I just have the inverse Fourier transform here, and what I'm going to get, if I had no epsilon there, so I put it here. Okay, what I obtain here is just a of x, f of x, something fixed. I just multiplied by a of x and write this in a complicated manner. But if I add the psi here, okay, I am starting to play simultaneously in the variable x and in the variable, the Fourier variable. Okay, and when I do that, since I have taken a very rapidly decreasing, it means that I am selecting frequencies. Okay? If you look here, what I could do is just to remove the epsilon here. Yeah. And what I am looking at is I am selecting some frequencies which are bounded more or less. You can think that you take A completely supported in this variable psi, and it means that you are looking to exactly to functions which are oscillating like 1 over epsilon. Okay? So for this problem, for example, usually so I have to select what is selected as an epsilon is exactly the epsilon n equal 1 over square root of lambda n, which is the size of the oscillation. And then with this approach, if you see that if you have no psi variable, you are back with the quantities there. Okay, so you are going to derive properties of quantities of that shape in order to connect the dynamics and the quantum evolution. Okay. And this relies mainly on what is called a Grove theorem. That if I look the evolution through my operator, so let's write it in Rn. If I let evolve my operators, okay, so I have it. I look this propagator because I mean it's scaled in a good manner, and I look to this conjugation. This is just a of x plus t psi minus. I'm not sure of the sign because I may have made something wrong. But the good thing is that you have so up to lower order term, the conjugation of A by this propagator is related to a flow. Okay, and my flow here is just xi maps x minus t psi. So the proof of the result in the classical case, in the Riemannian case, is based on this observation, on the fact that these operators, this propagator, they act on the phi n like a phase, but when I conjugate this and I make it apply to phi n, I find back r epsilon t, okay, equal a. Okay, I do nothing when I let this operator acting on phi n. When I can replace, in fact, here, I can make this flow appear. Okay, in the case of a compact manifold, the flow is the geodesic flow, and the fact that the flow is ergodic will generate properties of the limits of this quantity. Okay, so this is the basic idea of a theorem. Yeah, the proof of a theorem. So what happens in the case of contact manifolds, things are more involved, and I think that the result of Verder is really a beautiful piece of analysis, because I mean it becomes tricky to use this sort of approach for this problem. And what he's doing, Nino Benedetto, is different. He decides to use a symbolic pseudo-differential calculus which is adapted to the filtration. Okay? And why he is doing that? I mean, there is maybe a reason which is very clear, is that if you have this estimate, it means that if you apply a xg to phi n, it will be controlled more or less by square root of lambda n. Okay, if I take the first one. But if I take another one in an higher, in an element h6, for example, yeah, then I will need to make a lot of brackets, 6 brackets, and so the scaling becomes square root of lambda n to the power 6. Okay, so in some sense, you need, it's a multi-scale problem. Interestingly, this, in that case, you have a multi-scale problem. And the idea of the approach of Benedetto is to use theory of Lie groups and of representations on Lie groups, the Fourier theory of Lie groups, to get calculus which is containing the multi-scale realization of the vector fields that you want to do. Okay? So, what I'm going to do is mainly, so it was my introduction, I have the boards. I want to motivate the use of Lie group. Motivation for using Lie groups. I mean, Rn is nice. Why should we go somewhere else? Yeah. And then I write the second. And then my second part would be to explain the pseudo-differential calculus for this result. Yeah.
Since it was the end of your introduction.
Yeah, sure, perfect.
So I'm not sure I understood the conclusion. You saying that the classical approach to quantum ergodicity works in the case of...
It works for the equal one, they did it.
In general?
But I mean, if it was a direct consequence of what they did, I should have wrote a bit of it. You can ask Luc. I mean. So I think that there is a difficulty in higher dimension, which is, I mean, there is a difficulty anyhow, but what I claim is that there is a multi-scale problem which is intrinsic in this result, and that you have to, and one way to code the multi-scale the multi-scale feature is to use this formalism.
It doesn't work because of the multi-scale nature.
I mean,
easily because of the multi-scale nature, and that's what you're trying to do now.
So, yeah, I mean, maybe it's a philosophical approach, is that I have always thought that it would be better to take, that if I want to deal with this problem, I need something which is sorting out these two vectors and saying that derivative in x and z is not and y is not the same as derivative in z. Okay, and so that was my first guess, and I work a lot to construct a pseudo-differential calculus which is in this spirit on this group. Okay, and the point is that I was very happy with this result of, I mean, he's my PhD student, Benedetto, because using the approach that I was promoting, he has obtained a better result than Clotilde Fermanian. Better, I mean, in the sense that he's able to treat larger d, so d bigger than 1, okay? He's paying a price here, and he has to work a lot to remove these two. Yeah. Okay, but I mean, the intuition, what is, I mean, you see the intuition, it's a matter of intuition to get some calculus. I mean, so the differential calculus is something heavy, and you like to follow the main features of the problem. Yeah.
Sorry, Clotilde, I know this isn't what we wanted to be talking about at this point, but just to clarify, this is all the contact case, right? So the setting where it takes 5 iterated commutators to fill out the whole tangent model.
Yeah.
Is that open in the context of QUE, of quantum ergodicity?
Contact means that R equal 2, but if you have R equal 5,
yeah, R equal 5.
Yeah, for example, you have R equal 3 Engel manifold. Engel manifold should be done with this formalism. And the proof of Benedetto for what is called Heisenberg manifold, it works also for Engel manifolds and quasi-contact. So, but yeah, I mean, because of this structure condition. So you can do that in this frame. And the idea is to have the calculus that we construct is in this general case. Okay. And there was another question, yeah.
Two. One is that, would you mind explain again the multiscale? Like, how do you get the iteration, that iterating the number of iterations gives you the...
Yeah. The point is that this operator, I said it's a nice operator, so what it means a nice operator is that you can control.
With this operator or with the contact one?
It's the same, just in the contact case, you have n1 equal 2. Okay? So this is a generalization of that one. Contact case, I have 2 vectors. Here I have 2 square, and here I have n1 square. Okay? The point is that this operator, I mean, you need to be to know how it's improving the regularity. And this is another result of Monder. That's the remark. It's not a remark, it's the beginning of the point. But if I take this operator, and if I look to this equation, with this thing in a Sobolev space of order S, okay, then how is U? So U, so that's my operator symbol here. Okay, U will be in some Sobolev space of order something. If you were elliptic, you will be of order S plus 2. Yeah? And if you are just here, you have only these vector fields. Yeah, and that to get the other vector fields, you need to commute, and then you need to commute R times. Okay, you get of order S plus R over 2. So something S plus. So if R 2R, something like that. Okay. So you have a no, sorry. So it's 2 over R. So
if R is big, you want it to be worse.
Yeah. So it's yes. So I can write it like this. So I can write it like
probably S minus R.
Yeah, S minus R. S minus. No, but there is a fraction. There is a fraction. S minus R. Yeah. Okay. Over 2. Oh, okay, you lose something. Minus something. U is still more regular. So S plus something, and this something is smaller than 2, and it depends on the R. So 2 over R. Or 2 over R. Yes, if R equal 1, you have S plus 2, which is the elliptic estimate. So this is the sub-elliptic estimate. And this sub-elliptic estimate is proved by Ormander in the 70s. It's due to Ormander in the 70s. Okay. I mean, you are gaining less regularity because you need to do this bracket. Okay. And another way to see it is to say, okay, let us assume that we have this estimate. So it means that morally x1 square, x1 phi n is like square root of lambda n. But if I take xn1 plus 1, I need to do bracket. And for example, just here, if I take this one, so if I look to z, z would be 1 over epsilon x, epsilon y. Okay, so if this is bounded, you see that this, well, if you want to have something, epsilon square, so it's epsilon square z, is exactly, so if I can bond, if I obtain a good bond for this epsilon x phi 1 and epsilon y phi n, I will get something worse for this one. So it means that in my description here, if I know that my function is oscillating like 1 over epsilon here, that it will be 1 over epsilon square here, etc., and 1 over epsilon to the power r here. So this is the reason why it is multiscale. So you can encode all this in your test functions, and that's the way it's done by Coulomb-Verdier-Hillery-Trela. This is really tricky.
Another small question. Yeah. It seems that in all of these examples, that also where they were able to prove trace formula. This was trace formula with a very similar machinery.
Yeah.
And I wonder if it's also with the same structural condition, the same geometrical structural conditions.
Yeah, I think so.
It's the same.
It's for this subelliptic operator.
So it's the same. It's the same machinery when you do these iterations which allows you to.
The trace formula that I know, they are proved with the differential calculus of Benedetto, and there is also those proved by Lucky and. You have trace formula?
Trace formula?
No. Okay, so maybe you should not with me. It's out of my scope of knowledge. Yeah. So I wanted to discuss the motivation for Lie groups, and I am slightly making a movement to the 1970s. Okay, and the point is that this. I have made say something wrong. What did Ormander is to give this condition, Ormander condition, on the sum of square. So I have my operator, which is the sum of xg square from the first strata, and I assume that the h1 up to x1 up to xn are generating xn1 are generating all the tangent space by iteration of the Lie bracket. Then the operator is well closed. The operator is hypoelliptic. This thing about the sub-elliptic estimate has been proved by Rothschild and Stein in 1976. Okay, and what they do, in fact, is just using Lie groups. I mean, using Lie groups in this context is not new. It's a very old story from the 70s. Okay? In some sense, one way to motivate it is to say that, I'm doing PDE, so I like my operator. Okay, my operator maybe is that one, so I like this vector fields. This is the thing that are the more important in my problem. For example, if I want, so if I continue to say that this vector fields in my example, they are the important one, I want to connect my points in Rn with this vector fields x1, xm1, because it's my favorite ones. Okay? So it means that I am looking to represent a point x. I am going to try to solve the ODE and looking the flow at time 1 of the good vector fields. These my favorite vector fields, which are the one of the basis. So I'm going to take a basis of all my. So this is generating my tangent space. Okay, and I assume that it's well organized so that the first vectors are in H1. Okay, so above the point X. Okay, if I add these ones, I will be in H2x and so on. Okay? So I choose my vector fields in my frame in the basis manner, and then I say, okay, these vectors are the good data for my problem, and I try to I realize my point as a flow through using these vector fields. Yeah? And then if I look, my difficulty will come from the fact that if I compute the exponential of these things times the exponential of y1 n, I will not find the exponential of x1 plus y1, x2 plus y2, x3 plus yn. Okay? So if I play that game, I am constructing a non-commutative law, in fact, on Rn. I will find something, let's call it u1 un xn, and this u1 un is the image of x1. I mean, it states it's a polynomial in the variable x1, xn, and y1, yn, but it's a non-commutative law. And this comes from the Becker-Condal-Hausdorff formula. So, if you keep the intuition that you want to follow this flow because they are given by your problem, you arrive quite naturally in a non-commutative setting. Okay, so in doing that, I am back with Rn with a law. Okay, and because of the structure of my bracket of my commutators between my fields, which will be 0 after a certain level of commutators, it becomes a nilpotent group. So, if as soon as you have decided that you are not going to use Rn with a standard law, but with this non-commutative law, you open books for harmonic analysis about nilpotent Lie group, and you look what is possible to do. Okay? And actually, the proof of Challenstein of this subelliptic estimate, they construct a nilpotent Lie groups, which allows them to analyze this equation. Actually, I am cheating a little bit, because you may need to add some variables. So maybe you have to add variables to Rn. If I start like this with vector fields, which are like what we are, I could need to add some variables, and it's exactly what happens in the general case. Okay? But it was just for motivate to introduce the Lie group. Okay? And so, in fact, what you see in this story, in the literature, is that the community around Stein, they have worked on constructing a pseudo-differential calculus on Lie groups. Okay? And this has been there have been a lot of papers. So instead of doing my calculus like that, okay, in Rn, I decided I want to do it in another manner on the Lie group. And this is an odd idea. Okay, differential calculus on Lie group. But the point is that the first approach that people have developed is more based on the kernel of this operator. You see, here, my pseudo-differential operator has a kernel. My kernel is the integral. Here I am on R2, so my kernel is given by just 2 pi to the power minus d, the integral inside of this thing. Something which is the Fourier transform of A computed in x minus 1. Okay, the Fourier transform inside, if you want. Okay, there is a close link between pseudo-differential operators and Calderon-Zygmunt operators. And that's the way the people in the 80s have worked on that problem. So, Calderon-Zygmunt. So you look to the kernel of the operator and you assume that it is singular in a certain level, it has a certain level of regularity. Okay. I should not, so I am not going to mention all of the papers on the subject, but I want to cite a couple of papers from the 80s, from Pils, Meunier, Reiner, and Taylor, who are working, constructing a calculus on Heisenberg manifold, which are maybe the two contributions which are more symbolic. What I call a symbolic approach is it's an approach which focused on A and not on the kernel. So you can decide that your operator is defined by this kernel, that's true, but here the kernel has a special shape, and I can decide that this is the thing that is interesting for me, the A, and not the kernel of the operator in itself. Okay? Then there have been some, okay, I'm going to the 2000s, the years starting from 2000, and at that period there have been a reborn and interest for these operators, but really with a symbolic approach. So which A I can use for doing this, for constructing my pseudo-differential calculus. Okay. And for example, the problem, and it's not for example, the problem has been treated by Fischer and Brudzinski in 2017. They have constructed a pseudo-differential calculus on nilpotent groups, which use the harmonic analysis of the group. Okay, the fact is that on the groups, you have a Fourier transform, and they use this Fourier transform of the group. I will detail it later. Okay, so this is the first milestone that I want to write. And another interesting approach is used by Werner and Juncken. So here it's on the group, so it's flat. Okay, and Werner and Juncken, they develop something on a filtered manifold. But they have a totally different approach, which is coming from C12 algebra community. I mean, by many Kuhn's work. Kuhn's, I mean, it started with Kuhn's ideas, and it's based on a groupoid approach, which is not exactly the same, because in some sense you are considering symbols which are polynomial or polyhomogeneous polynomial. Okay? So I was I wanted to address these 2 points of view simultaneously, because this one is symbolic and this one is more centered on the kernel. Okay? So this is a kernel approach. And what we did with Fischer and Stephen Flynn is to extend this calculus on the groups to a calculus on filtered manifolds. So this we did last year, filtered manifolds. And the good things is that the two correspond. Okay? So we construct a calculus with a groupoid approach, with a C12 algebra formalism, and they obtain something that which is I mean, their operators are contained in our class. Actually, you can play the same game with Ormander calculus in the Euclidean case, and the Bors-Mandelius calculus, which has been introduced, I think, in the 2000s. I think it should have the 2014, and the Ormander calculus is containing the calculus of the Bors and Scandalis. So I want to cite another construction here of Androulidakis, Mosen, and Juncken, which is from 2022, and which is going beyond the case of filtered manifolds. Okay, so they authorize more singular properties of a tangent space. And clearly this approach is very strong because we have been able to prove the Elfer-Noriega conjecture, which was a long while. Okay, and so I mean the fact of using the harmonic analysis of the groups seems to be really powerful. So I have a couple of minutes to explain what we do and to be more concrete about this calculus. I go there. So what is the idea behind? The first idea is that you have a Fourier transform on the groups. Okay. First idea is that on a group, on a nilpotent group, you have a Fourier transform with a Plancherel theorem, which is just given by the representation theory of the group. So G hat is the dual of the group. It's a set of irreducible representation. So it's operators, a set of operators, modulo equivalence. So I don't want to have equivalent representation. Okay. And you have a Plancherel formula which tells you that function f of x, you can write it as an integral over G hat against a measure. And here you take the trace of phi of x, the Fourier transform. I have not said how is the Fourier transform. Okay, and to get the Fourier transform, you just integrate your function against the representations. Put a star here, the x on the group. So your group is like Rn, its measure is just the x. So if f in L1, I get a bounded operator on the space of the representation. So I should have put pairs on each prime. Okay? So here what I am saying is that there exists a measure on this set G hat. So it's a Plancherel formula. Okay, so that I have written like an inversion formula. I can find if I know the Fourier transform, and if it's regular enough, I will get back the function. Okay, so then it's quite natural to define operators like I did here, because here what I see is that here I have in Y I have in the Fourier transform of f. Okay, if my group was completely flat, it was Rn with the usual law by the Fourier transform is just here, exponential minus ixi y. Okay, and so what I just do, I don't do it. What are doing Fischer and Bruzanski is to say, okay, let's just introduce the symbol here. Okay, you can put a symbol here and say so sigma, what is going to be a field of operator on H pi. We need some, they define the good class, the good condition for this to make sense. And the formula would be the integral over G times G hat, the trace over, this is on the space of representation, the trace over H pi of sigma of x pi. Here, if I use this, the formula for f of pi, I get x y minus 1, so it's the x minus y that we had there, and f of y, nu of pi. Okay? So you obtain a quantization formula which plays on the Lie groups the same game than in the standard. Yeah.
Can you recover the classical Fourier transform?
Yeah. Yeah.
Can you tell us which?
Yeah. Yeah. So you, what is the, okay, so example, if
your G is just Rn.
Rn, pi of the set, the Rn hat is just the multiplication by exponential minus I x psi plus psi in Rn. Okay? You have only characters. Your representations are just multiplication by exponential I x psi Okay, and the space of representation is C. You don't have anything more. Okay, so if your trace becomes just multiplication, here you have a field of operator on C, it means a function, a of xi, and here you have exponential minus I, so x minus y. You have exponential I x minus y. Is it clear? No. So I write it.
I think so. The representation is multiplication by this.
The representation, so h xi is just C, so it's multiplication. Pi of xi is multiplication.
H is functions of C.
Exponential, because it's commutative, so it's a commutative group. So it's a character, it's a code character. So maybe you have met them. Yeah? And so it's just the same. This is the pi of x minus y.
So whenever your G is a billion, it's going to look like that. It's going to look like e to the ix xi.
Yeah.
But once it's non-abelian,
when it's not, it can be.
When it's non-abelian, your characters are going to be a bit more complicated to figure out the same function.
For example, for the group I had written at the beginning with the x, y, and z, okay, what you get is operators on L2, the 2 of RD, or you have two types of representation, with something like that, just in x and y, and then some operators on L2, which are, you have a formula for the pi. Okay, so you can calculate the representation of a group once you are given a group. Okay, and just to conclude with what we do for so I have not put some epsilon, but yeah, you have to play a game with the scaling in epsilon, but I will skip this part. And the second idea is to associate with my manifold some groups. What we do is the following. So I take a point x, I take a frame here, so my frame is my vectors x1, xn. Okay, and as soon as I have this frame, I associate. Okay, even without the frame, I define a Lie algebra just by taking the quotient of my hy x by hy minus 1x. Okay, so you get something like now you have taken your pieces piece by piece. Yeah, and with this frame you associate. Okay. So if I have a Lie algebra, because I take with the same bracket, okay. Since this was compatible with the Lie bracket, it means that I can. The Lie bracket in my tangent space is giving a Lie bracket on Gx. Okay. Once I have the Lie algebra, I have a group by taking the exponential of my group. Okay? And with a frame, I am associating a basis just by taking this vector class modulo this relation. Okay? I obtain the basis of my Lie algebra. Okay. So it means that here I had my frame, x1, x2, and I go back to my Lie algebra, and I obtain this vector, x1, x, x2, x, etc. Okay, so I have a sort of map between these two, between the straight, I mean the flat case, and my manifold. Okay, and so now how are we going to define the symbols? The symbols will be functions of, I take m in my x in m, and pi in the dual of this group, which we put m because. Okay, so above each point I have a set of,
correct that in this case the dimensions of the different are locally constant?
Yeah, exactly. Yeah, it's equiregular. So this is the filtered case. Is simpler, but that setting in. Here, my dimension of each of my group is good. Okay. Now I arrive to. I have this map, and I consider symbols which in X is smooth function in X, and in pi they look like Fischer-Wozonsky symbols here. In the group for pi, in the dual of the group above X. Okay. Then, since I am on a manifold, I am going to work locally. Okay. So we need a quantization formula that is going to depend on the frame, which is there, and also some cutoff function, which is localizing my function in U. Okay. So I have a cutoff, which is correctly taken. So it means that the first thing I do is to the cutoff on U times U. Okay. I multiply my function f by the cutoff. Now I am in U. In U, I can look to my points thanks to the exponential map. So at any point y, I can look how I go from x to y using the exponential the flow at time 1 of some vector that I will write exponential x of v. So v is in Rn. And what I mean here is that this is the exponential map of v1, x1, plus vn, x1. Okay? So I have this map, which allows to identify my point. So my point here, I'm going to identify them thanks to this sort of coordinates. They play the role of the coordinates. And I integrate so over Rn because v is in Rn. And here, if I look to my formula that I had before, no, it's no longer there. If I have here, you see that what is playing a game here is in some sense the inverse Fourier transform of sigma, because this is the trace of pi of sigma. When I fix the x and I integrate in pi, it means that I'm doing a sort of inverse Fourier transform. So I need a last function that I'm going to write, is that my sigma of x pi, they are the inverse Fourier transform of some kernel. Okay. So maybe it's not so clear. So what I am doing here is to
explain?
Sorry, I just yeah. And then I finish my and here I put this function, the kernel of v. Okay. So this yeah.
Can you explain what does it mean to exponent the sum of quotients? I don't understand the exponent here. Usually I think about exponent of a vector field.
Yeah, exactly.
As propagation of time.
Yeah, exactly. But this is a vector field.
But the sum of the quotient is no longer a vector field over
No, but here I am not in the quotient. I am in the manifold. The x1 they are not.
Oh.
Yeah. I am in the manifold.
So the exponent is before quotient.
So there are two exponential maps. There is an exponential map in the manifold for going to x to y. Okay, so I have to increase my x, my u. And there is an exponential map in Rn. If here I am in Rn, which is the one of the group. Okay. I can write it. It's here. This is the exponential map of the group.
This is over Rn?
Yeah.
Oh, I see.
So this is one of the difficulty of a game.
So the big one, the plus of the quotients, you chose already.
Yeah.
You chose already
here it's
basis vectors, and
yeah.
you just look at Rn.
So we work in that space. This one is playing in the space, the flat space Rn. the group, and the exponential map here is just for taking coordinates. So in some sense here, this is an element of the group.
Okay.
So I can integrate this function. I have to define. I should need to define correctly the kappa x, and then we can discuss this later if someone wants to. Yeah. But this is a function of Rn because it's the realization of my convolution kernel in the frame X, so it's living on Rn, and then I look to its Fourier transform in the fibers. Okay. And this formula gives you a symbolic calculus. So the theorem that the theorem that I should have written is that it's a bounded operator in L2, but this you see that if kappa x is very smooth, I mean I have not said anything about the sigma, but if the kappa x is smooth enough, you can just perform a sure test and you obtain that your operator is sending L2 into L2. Okay? You have some symbolic calculus, you have you can make a semi-classical version, and you can define with some proof. And so Benedetto has proved some Egorov.
So this whole thing has an Egorov theorem?
In the full generality, we have not written it, not yet. But I mean, there is no reason that there is not. In special cases, it has been written, but not in general. Yeah. Okay, but I should stop. I am too late. Sorry.
Thank you for your talk. Any short questions?
Are there elliptic parametrices?
Yeah. If you have a condition on the sigma, I mean, which is more or less.
Is the symbolic computation?
The symbolic computation.
Is local?
Sorry.
Is the composition of symbols local? Does the symbol of the product?
Yeah. I mean, the point is that they depend on chi at any order. I mean, if you compare, you take two different chi, and if you are in the semi-classical case, they differ at any order in epsilon. But in X, in the frame, only the principal symbol is the same. Yeah, it's order epsilon, but like in the Riemannian case. Yeah.
The symbol of the product of operators is the point.
It's the symbol of the product. Yes. Yeah. And the adjoint is the symbol of the adjoint plus the standard. And there was another question. Yeah.
So in the end, do you want to? You've got a new quantization where
yeah, I want a new quantization, and I have obtained it.
If you want to prove some form of quantum ergodicity
or
something like this, you would need to relate your quantization
to
the...
No, you don't need it.
So you would have a new statement for quantum ergodicity then?
So, I mean, it's the same statement than in paper, but what is Egorov theorem, it's Benedetto who did it, his Egorov theorem is different. But he has an Egorov theorem, which is giving exactly what you want to see is the right flow, the flow along this. We have your horizontal distribution, and then you have the red flow. And he has some Egorov theorem involving the red flow, and then he terminates. So, I mean, his proof is the proof of quantum ergodicity that he writes is just following the standard proof.
So,
yeah.
My question is, what was quantum ergodicity in this setting?
It was the fact that the red flow is ergodic. If the red flow is ergodic, then
Then what?
Then it tends to. I think he knows better than me.
Okay.
Classical measure is
Semi-classical defined using the standard quantization.
Yeah, but after, with both, because after you go back to the only in X, and the way you look to the frequencies disappear. You see?
I understand. Okay.
And so you get the same result, which is.
So it's not a semi-classical quantum ergodicity.
No, it's not a semi-classical quantum ergodicity.
Thank you.
Thank you. Any more questions? Want to thank the speaker again?